Weighted graphs. All right, here's where we place a number on the edges. So now we've got a weight. That's why it's called a weighted graph. Examples of weighted graphs arise from the graphs. Vertices of a graph are towns on a map, and the edges are the roads between the towns.
So, for example, that 12 could represent kilometres between
right.
two towns, whatever it is. So that's what the weight is.
That's what the weight is. Now, a tree is a connected graph that contains no circuits. Here is an example of a tree. There's no loops here, no circuits. We can't go from E to G. We have to go around the towns. A tree has no multiple edges. Simplest tree is a single vertex.
That is a tree.
Yep. A tree with n vertices has n minus 1 edges.
Another rule.
Okay. Minimum spanning tree. Here's where we try and minimise the distance between these vertices. Quite easy to do. And there is the rule. We start with the smallest length on the vertex. In this case it was number 3. And then we have to connect it. So we have to connect to either C or D. And we use, again, the smallest one that connects. In this case it's 5, 5 or 6, so it doesn't matter. We'll choose one of the 5s. We'll choose this one here. And then again, another one that connects another vertex. Well, we've only got A to go, and the easiest way to connect this one is through here, because that's the smallest one. So we get this minimum spanning tree that's shown in figure 23.23. Okay? A spanning tree is just a subgraph that contains all the vertices of the original graph into a tree. So we have to use all the vertices. A minimum spanning tree for a weighted graph is a spanning tree for which the sum of the weights of the edges is as small as possible. That's why we choose the smallest numbers all the time. Alright, here we have Prim's algorithm, which is a set of rules to determine a minimum spanning tree for a graph.
So I guess, these are the 3 rules that you've got to do to use it, but I don't think we need to go through it. You just be aware that you've got this.
Right. You can follow the steps. We're just going to do it with you as an example, which we've already done.
We'll apply Prim's algorithm here to obtain the minimum spanning tree for this graph. So then it wants us to write down its weight and compare the weight to the original graph. Now the original graph, if you add them all up, it all adds up to 50. Okay? So this adds up all to 50.
So that's the original graph.
Alright, so we'll start at point A.
Oh, it doesn't matter where we start. Well, no, we should start where there is the smallest number. So there's a 2 and a 2 on 2 edges. It doesn't matter. We'll start at A to B.
Okay, so we start here and then we go, right, we've got to choose this one here.
There we go. We've chosen that one. Now we need to connect either A to something else or B to something else with the smallest number on it. So A to D, it gives us 5. We'll connect that one there up.
There it is.
And then our next smallest
straight line, Mr. Denethor,
is number 3. Doesn't matter. So we'll go D to C. That connects edge vertex C. Now we have to connect either E or F. There's no point going A to F because that's 6. We've got a 5 from C to E, so we'll connect C to E. That's 5. We have to connect F. E to F is only 2, so we'll connect that one there. And that is our minimum spanning tree.
So they want us to write down its weight and compare it to the original. Well, the original was 50, and if you add all these up, they'll add up to, I think it's 17,
5 is
isn't it?
7, and 3 is 10, and 5 is 15, and 2 is 17. So that's the minimum spanning tree, 17 compared to 50.
So in a real life situation, we can just sort of say that, okay, if these are, let's say, roads 2 kilometres long, and we've got to lay cables there, we'd need 17 kilometres of cables.
That's right.
It could be internet cables or phone lines or whatever. We need 17 k's worth of cables for the 50k roads.
That's right. We could do the 50, but that's going to cost us more. So we'd rather do the 17. Now, there is a note. If you're ever asked to find the maximum spanning tree, you start with the maximum weight and keep finding the maximum one, adding to it. Okay, not the minimum like we've just done. 23 is your questions. Thank you.